Excellent. I hear reverbs. The microphone is on. Fabulous. Well, good afternoon, everyone. For the benefit of those online who don't know who I am, I'm Dr. Kieran Bjergström. I run a company called Quantum Technologies Associates, and we look at a variety of things, but a lot of what our work is around market positioning for quantum and around end users and their demand signals. We also work on the engineering of quantum hardware, particularly its systems engineering, its reliability, its manufacturability. I'm also the quantum lead for the Royal Institute of Navigation in the UK, and the Royal Institute of Navigation looks seriously at all matters of position, navigation and timing to all sectors. That's the maritime sector, which is the prevailing focus at this event, but also for civil aviation, also for smart cities and societies more largely. And we try to comment on where there are risks, where there's a need for solutions, and we also try to help inform industry and government on what could be done to solve those problems as a learned society. Today we're going to be talking about what is quantum P&T. This is a interactive session. We've got a small audience, so questions may be forthcoming. But I think to start this, my goal is just to sort of baseline what we mean by quantum P&T, why it's important, what demands we're trying to address. So let's start with why now. Why are we talking about quantum P&T at this conference? We've heard a lot about quantum comms and quantum computing and comparatively little about sensing, so I think it's worth testing whether it's a conversation worth happening. Is there a demand or risk that we're addressing? And I think the answer is plainly that there is. P&T risk and demand are both growing, and they're growing for different reasons. And better P&T systems are needed, and more resilient P&T systems are needed. And that's for a few reasons. So P&T vulnerability has been well articulated for the last few years. It is a more recent articulation. I'd say it's something that's come into focus over the past 5 or so years. And in the UK, at least, we had a seminal report called the Blackett Review on Satellite-Derived Time and Positioning, a study of critical dependencies, which is a government-commissioned review. And most importantly, it looked at what's the cost of P&T vulnerability. If you lose access to GPS or global navigation satellite systems more broadly, how does that impact society? And it had a headline figure that there was a cost associated with this of about £5 billion a day in lost economic value. So it's enormously significant. And then the downstream consequence of that is that if such a loss of signal continues, if such a loss of time in particular from GPS continues, you start to see many core aspects of society and of sort of operations fall apart, whether that's logistics, whether that's food delivery, whether that's refrigeration, whether that's digital systems. So it moves from a high cost to a strategic vulnerability. I'll show one more of these in a moment, but I think it's also worth noting that P&T is GPS especially derived P&T is a highly exposed system. We see extensive jamming and spoofing, and this is affecting the civil aviation sector, and this is affecting the maritime sector, and this is a website called GPS Jam, which shows you where spoofing is pretty much every day. It's got a little 24-hour heat map. Incidentally, green isn't good. Green is also bad, just not as bad as yellow or red, and I think a takeaway from a map like this is in most populated, busy, dense areas, you see significant GPS interference. And if you're using standard civil receivers, the type of inexpensive and ubiquitous technology that we rely on, this is the type of interference that will affect what you can achieve. And then, of course, over areas of sort of geopolitical conflict and contest, you see far greater, far stronger levels of interference, which would disable most civil systems. And this has impact. So we have a nice article from May 2025 where the grounding of the MSC Antonia was specifically attributed to GNSS spoofing. And I'll talk a little bit more about the impact of GNSS spoofing to the maritime sector in a moment. But it's not also maritime. We had this BBC article on planes having their GPS hacked, and I'll certainly go into that in a moment, and this notion that local sensors may be part of the solution. And I actually thought, this is one of my favorites, in May 2025, Vanity Fair had a headline article talking about GPS vulnerabilities. And when you know it's on a headline for Vanity Fair, you know it's important. It's entered the public zeitgeist then. So that's quite an indicator of how widespread these issues are. And on the UK, and I think this is worth noting, it's also something that's made its way into policy. We have something called the National Risk Register, where we describe the risks that the government is kind of tracking and committed to mitigating, and loss of P&T services is one of those risks, and it's a significant risk. It's not one of the the minor ones. So it's an escalating problem. There are a few ways to address that problem. From a Royal Institute of Navigation perspective, we have recently been developing ways to achieve P&T resilience for critical national infrastructure, especially how behaviors and how processes can mitigate this risk. And I just want to highlight that to say that it's not entirely about technical solutions, it's about being aware of P&T vulnerability and then changing behaviors as well and changing awareness to mitigate those dependencies. We've produced a P&T resilient checklist that organizations can look at with a main focus on CNI and to start with aviation. There was also quite recently, last year, a report on GPS spoofing from the Ops Group, which is a civil aviation body. And it drew out a few conclusions regarding the severity of GPS jamming and spoofing issues. Firstly, they highlighted that it was very significant. It was extremely significant, and this was to flight safety, but this was also to operations. This was to the maneuverability and handling of aircraft. This was to air traffic control. So it wasn't a siloed impact. It was a widespread and extremely significant impact. And they went in to describe a little bit more about how this impact manifests, the consequence of jamming and spoofing on a platform. One of the really important points that they noted is that it renders core warning systems that pilots rely on as effectively useless. And this is a change, this is a degradation that exists during the period of jamming and spoofing, but also after the period of jamming and spoofing, and for a variety of reasons. Sometimes it's because they are contaminated with false data, and it all appears hunky-dory from the perspective of the navigation system, but it is in fact all misleading. It's all incorrect. But other times it's just by overwhelming human factors. False alarms all the time, noisy alarms all the time, an environment where you can't actually perceive or manage the information being given to you. So you just turn it all off, broadly speaking. You silence alarms and you try to continue flying. It's a rapidly increasing threat as well. So there's about a 500% increase in jamming and spoofing incidents in aviation in the last year. We don't have an equivalent figure for maritime at the moment, although there are a couple of reports, industry body reports looking into it. That means it affects around 1,500 flights a day, a serious incident of jamming or spoofing. That's quite a lot. It's a really significant impact on civil aviation. I mentioned earlier that some of these systems are degraded post-spoofing and jamming as well. Some of these systems are degraded even upon landing. A hard reset of these systems doesn't fix the issue, so it requires maintenance. Technical guidance on what to do when you have a spoofing or jamming incident is missing. It's underdeveloped, and there's a lot of work being put into actually enhancing that at the moment. And I think a really important point, and one important to the maritime sector as well, is that there was a view that over-reliance on GNSS and GPS for all navigation as the master source of positioning and navigation information is a serious problem. And it should be noted that from a training perspective, GPS is a secondary navigation source for aviation. The primary navigation source is the inertial data and it's the instruments. But that doesn't change the behavior of pilots, actually. There is a culture of reliance on GPS. This is relevant to maritime too. The master navigator is using non-GPS-based information for navigation at a certain level. You have a master lookout as well, but there is a reliance on the digital systems that are available, and that breeds a type of dependence. And I think a last point is that this is all collateral damage as well. A real conclusion of this report is that there's no evidence that any of this is targeted at civil aviation. This is spillover from conflicts and from other impacts. So we can wonder what would happen if it really was targeted at aviation and maritime, but we can also just observe that even in the background, this is the level of impact. We might think that civil aviation is leading the charge in understanding the impacts and severity of this, but they're not. Maritime sector has actually been looking at this since 2008, but it's perhaps done a little less about it than other sectors. And there was one particular trial in 2008 that was published. There have been numerous trials since that aren't really in public material. And it drew many of the same conclusions. If you spoof or jam GPS, vessel bridge systems degrade in functionality significantly, and you have an overwhelming number of alarms that cause that overload all of the operators, and indeed that the same attacks carried out on shore-based infrastructure that interface with vessels result in similar degradation. So the shore is vulnerable and the platform is vulnerable. There's a need for resilience across the board. It also has second-order impacts such as AIS, which is the system by which ships report their location as they sail. This data becomes unreliable. So you start to lose track of where objects are in a complex and congested sea space too. So it has quite a few knock-on impacts. One targeted non-quantum solution that has been looked at a lot in the maritime domain is ELA-RAN, which is an RF-based terrestrial signal system, and it should be noted that there are competitor systems. This has seen to be providing a competent alternative, but it's a large and costly piece of fixed infrastructure and a new broadcast signal, so it has its own vulnerabilities and it has its own challenges. So I just thought I'd pull this up as well. This is the GPS jamming in this area yesterday, as you can kind of see. It's not too bad here. There's a bit of interference, but it's not awful. Some red spots, and then you can see this is how the wider world looked, or slightly wider world looked yesterday. So interesting to see these day by day by day, and you notice that there's actually just a persistent trend of significant interference. This is all based on civil aviation data as well, so if you're on the sea, it would actually be a bit worse than this. That was the risks. That's the stick. Why is PNT really vulnerable and why do you need to fix it? But I think we should also talk about that it being a key enabler. And I think this is where quantum in particular has a unique advantage. It is in particular an enabler for autonomy. As you move to autonomous systems in an environment where you can assume by default you're going to face vulnerabilities, you're going to face jamming and spoofing, you need systems that have resilient PNT with strong holdover, independent of the threats they face. And that points to local positioning solutions, not signal-derived positioning solutions that could enable autonomy in cities, in vehicles, in aircraft, in ships. This is a Norwegian vessel that is the fully autonomous cargo vessel. And also in domains where you simply don't get signals, such as subsurface. You're not going to get a GPS signal there, and autonomous operation of those platforms requires local sensors. These demand signals also reflect a growing industry. So sort of two sides to this slide I want to talk about. Firstly is the fact that GPS, whilst vulnerable, is a growing market. These are numbers regarding the number of GNSS receivers that are currently out in the wild for different sectors, and these cover all sorts of qualities. These are receivers that are the size of a grain of rice and cost $1, through to receivers that are highly certified for special environments and cost $10,000. But you're seeing really significant growth in the value of the GNSS segment in general, and that means there's a growth in dependence on PNT data. That is something that the quantum industry can tap into, but also that highlights the importance of this. And there's also, I think, a growing focus on having alternatives to PNT. If you spoke about position, navigation, and timing, or GPS overdependence 5 to 10 years ago, there was really limited awareness that this was an issue and that this was an important issue. And I think that that's changing, and it's changing partially because of jamming and spoofing risks, but also because of a clearer and better articulated demand for sovereignty and assurance, including nationally independent PNT. We have this astonishing thing with GPS because it's a system the Americans built and footed the cost for, and it's free at the point of use for anyone in the world. But that is also a reliance on maintaining access, and that's a unique risk. And we see with LEO constellations, other space-based services, that people are trying to mitigate that in the space domain, but it's also something that can be mitigated more locally. And on the topic of local PNT, there is a view that there needs to be PNT of last resort. What do you do if there is a really catastrophic situation? This may not be intentional. This may be space weather, for example, taking out a significant part of the space segment. What do you return to as a baseline PNT capability? And this is really only provided by sensors that you can control in an environment you own. And there's also a regulatory push. So there are standards growing on required PNT resilience, and there's standards growing on mandatory backup systems, and being able to prove that. So we have a growing sector, we have growing risks, and we have drivers that clearly articulate why independent solutions are needed. So that's the why now. Quantum is seen as part of the solution too. And I think that's a really important thing to emphasize. It's seen part of the solution globally. This is just I stole this from GQI. They gave me permission to use it, but this is a nice map on government-driven funding of quantum commercialization. You can see the breadth of investment, and I think we're probably all aware of that here. Most of this is computing, to be frank. a little bit of this is sensing, maybe 10% of it is sensing. So overwhelmingly computing, but sensing isn't being forgotten about entirely. And I think we have a belief that quantum will provide new levels of performance for core forms of position, navigation, and timing sensors. And there's sort of three categories there there are three categories and some more. I'll go into them in some more detail. I'll leave that point for now. But I think the real thing is, from a scientific perspective, we see quantum offering a new level of performance. So there is reason to believe that quantum can outpace anything that's currently being developed. And many of the current technologies are also highly mature. So it's not the case that we think there's going to be incremental improvement, and in 5 years, the box today will be 1.5 times better. There is a need for something new, something innovative to bridge capability. This is a nice image actually from the Quantum P&T Hub in the UK, from University of Glasgow, and they've tried to make some predictions and some models of what a fused quantum system might provide in terms of positioning holdover, in terms of navigation data. We don't need to go into the numbers really on the axes, but the real point is they see a significant step change, really a greater than order of magnitude improvement in holdover capability, the amount of time you can go without GPS when you have an integrated quantum system. So there's a risk, and we think that quantum is a solution. And I think, why now? Going back to that question, the most important part of why now is that there are mature quantum systems that are integration ready today or very soon. And I know we have some people working on magnetometry in the audience, so they'll see where I'm coming from for that. There can be an overperception that quantum systems look like this. This is from the US Naval Research Laboratory, and you can see that it's a lab-based optical bench. It's got lots of interesting tech in it. It's not integrated, and it's certainly not fieldable. I'd say this is not representative of where quite a lot of quantum sensors are today in the P&T domain. Of course, there are new prototypes that look like this, but most of them are further forward. You can then have things like this. This is one of Exale's current cold atom platforms, looking at having these inertial navigation systems that are super precise, super valuable for big warships, probably big strategic platforms, and you can sort of think that they're roughly integrated. This looks much better than the top picture, but it's certainly not a sort of a composite device that you could buy as a product. And some things are there, but actually quite a few things are considerably more mature. And they're products like this. They are fully integrated, fully packaged, commercially available systems, whether for timing, like Inflection's Ticker product at the top, magnetometry, such as Q-spins and Q-controls products, or even inertial navigation systems, such as CPI's product over there. And there are plenty of other manufacturers. So we're at this point of maturity now, which we haven't seen previously in the quantum industry, and that means that it's time to pay attention to this, because whilst the systems are becoming integration ready, integrators certainly aren't quantum ready, and end users aren't quantum ready. They don't know what's coming down the pipeline, and they don't necessarily have the processes in place to be able to accept, procure, and include these systems on their platforms. So what do we mean by quantum readiness? I sort of created this list of questions. I think these are the sorts of questions that an organization that's quantum ready or an integrator that's quantum ready might or should be able to answer. These are the sort of things that they should be able to respond to. Where and how is quantum providing advantage to them? What does that mean for its integration? What new requirements are there that they need to set and formalize and describe in order to procure these systems? Because ultimately, without a formalized requirement, they probably don't have anything to procure against. They don't have the justification. What does integration mean, and how tightly is quantum integrated? Is this something that's now a fundamental part of their system-of-system architecture, or is it something that sits outside separately? Whose problem is that to solve as well? I think that's a really interesting question. Is that something that they're going to solve? Is that something a supplier is going to solve? Is that something the quantum companies are going to solve? I don't think that's really understood just yet. And also the data problem. We can talk one thing about having really brilliant new sensors, but actually they also output slightly different and slightly nuanced data compared to traditional P&T sensors. And how really do we integrate that and derive an overall solution? And lastly, the boring but important things. How do we test it? What's the verification, validation, and assurance strategy? How do we get the right tick so we know that we can buy that within a certain bounding of risk? Are there security and safety issues? Are there compliance issues? Is new organizational expertise required? I know we've covered points like that in some of the other presentations, so I won't labor on them, but I think this is what a quantum-ready organization might be able to think about, might be able to answer. And it's not just incumbent on the quantum industry to understand this. This is also needed by the tier 1 suppliers, and the end users. Because and it's a point I'll make later, but I think it's perhaps worth seeding that quantum suppliers, quantum companies probably aren't tier 1 providers. Probably tier 2 providers with at least one layer of integration between them and the end user. So let's talk a little bit about P&T then. These are the sorts of systems that sit in what I broadly call resilient P&T. It's a system of systems, firstly. It's not one source, it's not just GPS. We have space-based systems, and that includes GPS, that includes low Earth orbit, that includes augmentation systems that have ground and space elements. And these are, how you get your normal GPS ping, how you get your blue dot on a Google map. You have terrestrial radio frequency systems. These can be long-range systems like ELA-RAN, largely phased out but coming back in certain areas. These are very, very long-range, very high-power systems. But you can also have short-range systems, guidance approach systems used in aviation, and similar systems around port and harbour approach for maritime. And you can even have shortwave beacon systems for other purposes. This can be as short-range as positioning systems in malls, for example, but not so relevant to maritime. You have local sensing, and this includes your inertial navigation. So these are accelerometers and gyroscopes telling you your motion, from which you can start to integrate back your change in position. And these can be odometric systems. These, as simple as the odometry counter, looking at your the rate at which your wheel is spinning, and so far, thus how far you've gone. Or these can be odometry systems that work through water, or they can be visual odometry-based systems. And you also, importantly, have map matching techniques which take a variety of sensors and understand where you are based on a relevant reference map, and you can have timing systems, local clocks, and timing systems are perhaps the most critical to all of this. You have a variety of enablers in this. You have data fusion techniques, processing techniques. You have integrity monitoring, and this is a bit that's often not spoken about. It's one thing to say you have positioning information or navigation information. It's another thing to say how good that is, and to be able to monitor that in real time. And indeed, if you're delivering P&T data to a platform, you're normally required to provide with that a bound on your confidence. What's the likelihood that your P&T data is misleading? Understanding that is not a simple engineering task. So that's another output that these sensors will need to provide. And there's, of course, a security element to all of this, to ensure that your new P&T data streams are secure and are usable and are assurable. And the last piece is P&T situational awareness. This is sort of the last part of the system of systems for P&T. This tells you what threats you might be experiencing. And it's not at all a simple thing. This includes ground-based reference stations that try to understand what the threat environment is and may communicate that out to other platforms. And it can include local sensors that tell you if you are being jammed or if you are being spoofed and try to help you understand what to do in those cases. Quantum sort of addresses all of these in one way or another. In the space segment, Quantum offers new sensors, especially in the form of better clocks, which can improve the performance and the positioning capabilities you can derive from GPS LEO or SPAS. Terrestrial, again, probably clocks on large, long-range systems such as ELA-RAN. These systems do ultimately broadcast time. All GPS does is broadcast time. So if you want those systems to be resilient, you need a way to locally, with long holdover, provide time. It's sometimes missed, but these systems also often tend to ultimately depend on GPS. So your LEO constellations, for example, often piggyback of GPS for their time. And your terrestrial RF systems may be doing exactly the same, just somewhere onshore. So local timing is critical to those. And then on local sensors, this is, I think, where we most see the impact of quantum tech. We see new accelerometers, new gyroscopes, and gravity and magnetic sensors for map matching, as well as illumination techniques for visual approaches. And there's clocks, of course, in that as well. We may also see quantum affecting the enablers piece, the P&T situational awareness, and the data fusion. I think the case is yet to be made whether quantum has a role around data fusion or processing, but it certainly has a role around security. And we've heard a lot about QKD here, but it does fit there, and there is a need to, as sort of a backbone to a lot of this, to ensure that you have secure data and communication. On P&T situational awareness, there's a sort of a niche requirement there for quantum, and it sits around Rydberg sensors in particular, having more ways to monitor the RF spectrum and to localize whether there are disruptions and then where they're coming from. And I think we can sort of see this in the diversity of solutions that quantum P&T offers. It's not one solution, it's a whole set of new technologies that are being added to the system of systems that can address the PNT problem. And I put quantum comms and quantum computing on the outside because they don't directly address these problems, but they do support the secure delivery of that data. And we can break that down some more. I'm not expecting everyone to read detailed text on a slide here, but I think we can see that across pretty much all local sensing modalities, these are the specific types of sensors you see integrated on maritime platforms and on autonomous vehicles and on planes. There are, in most cases, an impact that quantum will have. Some of those are very low maturity, and some of those are questionable in their level of impact and are still being investigated. Quantum radar is a good example. RF illumination techniques have some theoretic potential, but they haven't really materialized so far. But on the other hand, there are areas that are high maturity and have already shown extraordinary potential, and I think magnetic sensing stands out amongst those. And gravitational to a degree, although there's a lot more to do on the maturity front. And on the timing front, at the end of the day, those products exist today. Almost all future high-performance clocks are what would be termed broadly as quantum clocks. And that changes what you can do in a local environment. And it could change the cost point and the miniaturization as well. It could change what is currently a $100,000, $150,000 backup unit into something that's rack-mounted and maybe $10,000 to $20,000 in due course. And I think it's also interesting to note that this is a family of technologies. So we've sort of seen a variety of PNT use cases, and we've seen a variety of ways in which quantum chips away at them. But actually, this is a coherent set of underlying technology platforms that are being developed by the quantum sector, which have PNT benefits. That includes cold atom systems, which provide accelerometers, gyros, gravimeters, and various types of clocks. You'll notice clocks are in pretty much all of these. Warm vapor systems, including the magnetometric systems, but also Rydberg systems and things like atomic spin gyros, quantum optics systems, and illumination and trapped ion systems to a degree. So the quantum sector brings in a whole new range of technology platforms, and PNT technologies are one of their outputs. It also introduces novel supply chains. Some of these are vulnerable, but not all of them. In particular, we see weaknesses around the laser supply chain, and we see weaknesses around mechanical supply chains, control electronics, and coatings. These are areas where the quantum sensors depend on elements that are fundamentally different from that which is being used in the classical PNT supply chain, and where there are issues of availability and there are issues of single source of supply. I think to sort of move forward from what quantum does then, we've spoken about why we need quantum PNT, and we've spoken a little bit about how quantum PNT makes an impact and where quantum plays a part, but it's worth talking briefly about how you bring some of this together. And this is also a large gap. It's not a gap in hardware development, it's a gap in engineering capability. What we need is an approach to quantum systems engineering, not just to the development of quantum PNT sensors. You can see a nice picture of the USS Iowa in the bottom right. It's currently it's a picture of a broadside from the top, and this is the type of platform where you may be deploying a quantum PNT system, and it has enormous dynamics. The ship is rocked off to one side with heavy vibrations, with heavy motion, and creating something that is rugged enough to survive and continue to output data, to survive and is continuous through those types of events is an enormous engineering challenge. It's a far cry from a lab, and it's even a far cry from most fieldable environments. It's an extreme environment. And whilst this is a military example, very severe sea states, for example, can create a comparable situation for the maritime domain. So you do need these sensors that can survive irrespective of the platform environment you put them in. And there's also an understanding of how, for the integrated system, you maximize the overall performance and quality. There's this notion in systems engineering that good plus good does not necessarily equal good. So without careful integration, without careful understanding of data fusion, you may end up in a situation where by integrating a variety of very high-performance systems that independently have strong capabilities, you actually undermine your overall system performance. And that is a real lesson into investigating the data fusion aspects for quantum PNT. At a broader comment, I think this reflects a gap in systems engineering in the quantum industry, where at the bottom of the systems engineering process, where you're looking at detailed design and integration and system and subsystem testing, there's a very high level of maturity and they're very rigorous processes. But at the top level, where you're looking at stakeholder requirements and ConOps, and also system validation and handover, there's a little bit of a gap. And this is only really addressed through the direct involvement and engagement of the end user community and of the system integrator community. This is where the knowledge is not in the hand of the quantum developers. And this also leads to notions such as trade space analysis, trade-off space analysis. And it would be marvelous if something like this could be undertaken for the maritime domain and for maritime P&T in order to understand what the axes of value are and how you relatively rank those. Because there's no world in which a perfect product is delivered, so informed trade-offs need to be made with respect to the technology and the use cases and the needs. So having spoken quite a lot now about what quantum is, and perhaps a bit about what we need to mature it, I think it's worth talking about adoption hinges and KPIs too. What does the industry actually require in order for quantum to become convincing and to be procured, to have a value argument? On the value side, I think that's relatively simple to state. The first thing is that quantum needs to offer quality of performance in addition to what's already available. That's always true. And that may be in the form of doing existing things considerably better. Although it's a bit hard to do better in P&T because the baseline is GPS, and GPS is very much good enough for everything. So it might be being able to perform sufficiently well for intervals when you're in a denied or spoofed environment, or to aid recovery. The other thing that quantum can look at are additional features and additional capability. So considering map matching approaches and considering the other uses of those sensors, what else can a platform do if a quantum P&T system is introduced? There is value also materially in risk reduction and pricing that risk reduction. There was a presentation earlier that mentioned the way in which the insurance industry is beginning to price in quantum risk. In a very similar way, the insurance industry is pricing in P&T risk and risk to P&T disruption and jamming. And that risk will be priced in far sooner and far faster than new systems will be implemented. So the lag time on mitigating risk is much greater than the lag time in risk being actually priced and brought into view. And there is a straightforward argument around cost reduction, whether that's upfront cost reduction or through life cost reduction. Unfortunately, this is where quantum typically falls short. It is at the moment an extremely expensive technology, and it's an extremely bespoke technology. So it's quite unlikely that it's going to be offering new value points and new cost points at an initial stage. If there is a weight of demand, this may change, but not immediately. There's also a need for building confidence in the companies providing a quantum technology. I remember once I was speaking to a former Navy captain about quantum technology and briefing him on its capabilities, and he mentioned very clearly that you could provide the technology that met all of their requirements, that exceeded everything they have today, but that really doesn't mean that they'd be able to procure it. In fact, they would still want to use the old system that they'd been using for hundreds and thousands of hours of real use time that they knew the full behavior of, and they knew what to do if it failed, and they knew how to understand the data they were receiving from it and how to repair it and how to replace it. So there's a need for credibility and heritage in the companies, and that's in their technology, but also in their behaviors, in the notion that you'll be able to support that technology for a long time. So that's the longevity and the capacity to deliver, and also in the ecosystems that surround these technologies, the supporting businesses, the supporting data models, the supporting assurance processes that make it possible to procure, use, and keep on using these technologies. And this is a problem solved between the quantum industry and the maritime sector and the system integrators. I think, though, we can probably signal a hopeful message here. When we were talking about quantum technologies just a few years ago, systems were largely lab-based, they were not very fieldable, and there were fundamental questions whether you could make them rugged and whether you could develop the sorts of systems necessary to create commercially valuable quantum P&T systems. Those risks and concerns have largely been put to bed now. The systems are reaching a sort of a fieldable level of maturity rapidly. These wider concerns remain, but we're seeing considerably more trials and demonstrations of quantum PNT systems in both the military and civil domain. In fact, I think the first civil trial of a quantum PNT system is due within the next month or so, which will be in the context of a vessel for voyage. But it still sort of starts to build that heritage. And we're also seeing much stronger collaborations between the quantum industry and systems integrators. And this relates back to the point I made earlier regarding whether or not a quantum company is really a tier 1 supplier. Probably isn't. It's a company that provides sensor technologies along with a gamut of other systems based on their technology platform, and it's up to mature and very experienced systems integrators, whether those are in the defense or civil sector, to integrate that and bring that to market. And on the final point of test validation and assurance, that understanding is coming. It's coming predominantly in the defense domain at the moment, but there are more and more trials and more engaged activities with defense end users which are proving their understanding of the system and allowing them to start to set requirements and define how they would like to be able to assure and procure these technologies, to define the performance indicators or the requirements against which they need to sign off on procurement. And it's through that direct and fulsome engagement that we can assess and set those processes, and also start to inform standards and certification bodies. So it goes one step further. That's a user-driven process, and it's typically the end users who promote the right certification requirements up the chain to the relevant bodies. So there are challenges, but there's also an enormous rate of progress, and there is enormous potential for quantum technologies to address the most pressing PNT challenges at the moment. And I just sort of reflect back on this this image to sort of close this sort of information session, in that we see a global investment in quantum and we see a global risk in PNT, and these are connected things. There is a recognition that that the solution that quantum provides is important, it's strategic, and that it's moving quickly. So this rate of acceleration is, there's a rate of acceleration in the investment as well. And there could be, I think, very easily a parallel image for PNT technologies because it sees a similar trend. I shall pause there. I think rather than having a workshop, I'll take any questions if there are any. Yeah, absolutely. Mm-hmm.
Sorry, thank you. Yeah, because this is the things that I'm aware of in maritime. I think this is very important. And do you think when is the faster years that we can get it into medium or high maturity?
So quantum illumination and LiDAR, I would generally rate at the moment as having a relatively low maturity. It's predominantly lab-based with controlled fieldable experiments, but it's not in a sort of it's not being utilized in a way that demonstrates its performance in a sort of what would you call it, a complex real-world platform with all of the obscurance and all of the platform noise that comes with that. It's still at this stage a relatively early technology. For the maritime domain, I think it also remains to be proven where exactly the benefit of quantum illumination comes. The advantage of quantum illumination is typically, again, imaging through highly obscured environments, such as through smoke or through a lot of spray or water, and that may have some sort of, I would suggest, specific or niche use case specific benefits for the PNT sector. But I think that we will see greater benefits sooner from magnetic map matching, from gravimetric map matching, and also from plain old inertial navigation. As in both cases, for much of the oceans, gravimetric and magnetic maps have a high level of uniqueness, so you can position quite accurately based on them. And inertial sensors are already the backbone, are already a complementary system in classical platforms, in maritime platforms, and their augmentation with quantum is relatively straightforward if you want to achieve ultra high levels of performance. And that's sort of the last point I'll make on that. From a market perspective, I think that almost all of the first tier use cases are around very high value and bespoke technologies for high value platforms. There is a need to establish an initial small volume of demand if the technology's manufacturability and cost to manufacture is going to be scaled. So we will probably start with some of these technologies in very small unit numbers at a very high price point, and that will gradually create a pathway to creating wider uses. So for LiDAR, I think it's a matter of finding the very high value and specific use case that could justify a bespoke integrated system with perhaps single numbers of units to begin with. And that probably reflects the maturity and the engineering challenge of deploying it. I'd be very interested if you have a notion of what that use case might be.
Yeah, exactly. So yeah, because we did quite a lot about LiDAR in the port of Dover, and currently we have in my project in transit we have cybersecurity and also sensing work package with also looking at the LiDAR thing. So yeah, I'm just curious how mature is it? But you mentioned about it's like a chicken and egg, isn't it? It depends on the
So what was the use of LiDAR in that context? What was LiDAR? Was that shore-based or ship-based, and what was it being used for?
It was both actually. So in the port they have within the port of Dover itself and also in the ships. So yeah.
So I think that your shore-based use case is a really interesting one because that could help situational awareness, sort of independence of time of day, independence of weather conditions, including in very foggy conditions, improving immediate awareness of the environment around the port. And it may also, and it certainly will in due course, be relevant for autonomous platforms which are highly dependent on LiDAR ranging.
Yeah, exactly. Great. Yeah, very interesting talk. Yeah.
Excellent.
Thank you. Yeah.
Thank you very
Keep
much.
in touch.